Good day, I'm Norman Wappinger. Today we're going to look at a very classical theorem from ancient Greek geometry called Heron's formula. And we're going to connect it to this triple quad formula that we established last time, which I'm trying to convince you is one of the most important formulas in mathematics. Along the way, we're going to talk about a nice relation called Archimedes' function. In fact, we're going to attribute some of these ideas back to Archimedes. Okay, so the context that we've been talking about is that of one-dimensional affine geometry. A very simple situation where a point is just represented by a rational number enclosed in square brackets. We introduced the idea of the quadrants between two such points. If we have the point 2 and the point 5, then the quadrants between them is 5 minus 2 all squared, which would be 3 squared or 9. So it's the square of the traditional distance. And we're trying to convince you that having this purely algebraic point of view, not involving any absolute values or square roots, is preferable. Okay, so if we have 3 points on a line, say A1, A2, A3 in some order or another, we can define 3 quadrants. Q1, the quadrants between A2 and A3, Q2, the quadrants between A1, A3, and Q3, the quadrants between A1 and A2. And then the second most important theorem in mathematics, I claim, is the triple quad formula, which establishes the relationship between these 3 quadrants determined by 3 collinear points. And this is the relation. Q1 plus Q2 plus Q3 all squared is twice Q1 squared plus Q2 squared plus Q3 squared. And this motivates us to introduce what we might call Archimedes' function, which is the following expression. We'll call it A of Q1, Q2, Q3. So by definition, it's the difference between the left and the right-hand sides of the triple quad formula. And we saw that a little bit of algebraic manipulation allows us to rewrite this in a asymmetrical but somewhat simpler fashion as 4Q1 Q2 minus Q1 plus Q2 minus Q3 all squared. And this was one of 3 possible different asymmetrical rewritings. We could have also said 4Q1 Q3 minus Q1 plus Q3 minus Q2 all squared, or 4Q2 Q3 minus Q2 plus Q3 minus Q1 all squared. So that's what we're going to call Archimedes' function, and it's of course intimately connected with this triple quad formula. Alright, so here is a very algebraic, in fact an arithmetical theorem that gives us another reason for appreciating the importance of this triple quad formula. So the theorem is that if D1 plus D2 equals D3, and you can think of these as just being numbers, rational numbers, and we define Q1 to be the square of D1, Q2 to be the square of D2, and Q3 to be the square of D3, then the relationship between the 3 squares, Q1, Q2, and Q3, is that they satisfy the triple quad formula. Namely, A of Q1, Q2, Q3 is 0. So this is telling us how to go from a linear relationship between 3 numbers to a quadratic relationship between the squares of those 3 numbers. In fact, in that previous video, when I asked you to essentially derive the triple quad formula, those of you who did do that exercise, and I hope it was many of you, will very likely have found this argument, that basically we start with a relation like this and then we transform it to see what the relationship is between the squares. And along the way we discover the triple quad formula. So let's see how that goes. So suppose that D1 plus D2 equals D3. We want a relationship between the squares. So it makes sense to square both sides of this equation. D1 plus D2 squared, the square of the left-hand side. What does that give us? Well, by the binomial theorem, the square of d1 is q1. That's what we're assuming. And then we have twice the product, and then the square of the second term is q2. All right, so that's the square of the left-hand side here, and the square of the right-hand side will be q3. So this linear relationship is now transformed into this relationship between q1, q2, q3, and still d1, d2. We'd like to get rid of the d1, d2 and just have a relationship involving q1, q2, and q3 only. How are we going to do that? Well, a little bit of algebraic manipulation. What we're going to do is we're going to bring all the q's to one side and all the d's to the other side. And then we're going to square things again. All right, so we take q1 plus q2 and we subtract q3, so there's the left-hand side now. And we bring this 2 d1 d2 to the right-hand side, so we have minus 2 d1 d2. And now we square both sides to get q1 plus q2 minus q3 squared equals the square of this, which is 4 q1 q2. But that's exactly the triple quad formula in that asymmetric form. So a of q1, q2, q3 equals 0. I remind you that another form for a of q1, q2, q3 is 4q1, q2 minus q1 plus q2 minus q3 all squared. So this implies this. Right. This is a purely algebraic, in fact an arithmetical result that's intrinsically independent of geometry, even though it's motivated from geometry. It's telling us how to go from a linear relationship between three things to a quadratic relation between the squares of those three things. Okay. And the triple quad formula naturally occurs here. It's a very fundamental kind of thing. So it's a very good example of useful algebra. So if you're a high school math teacher and you're doing some algebra, getting your students to do some algebraic manipulation, this is a great kind of direction for them to experiment in. Something actually interesting and useful involving some algebraic manipulations. All right, now I want to introduce to you an algebraic variant of that previous theorem. A lovely identity, which we are going to call Archimedes' formula. Now, did Archimedes know this formula? Well, I'm not sure. My motivation for calling it Archimedes' formula is that we'll see that this is intimately connected with a classical result called Heron's formula in geometry. And it's known through Arab sources, not directly but only indirectly, that Archimedes knew Heron's formula roughly 200 years before Heron did. So we don't know what Archimedes' understanding is. A lot of the works of Archimedes have been lost or only partially known to us. So I'm going to take the license of naming this result in honor of Archimedes. In my view, Archimedes does not have enough formulas and theorems named after him. So we're going to remedy this situation just a little bit today. Okay, so what is this lovely theorem? It's, again, pure arithmetic or pure algebra. Okay, so suppose we have various quantities, d1, d2, d3, and q1, q2, and q3. Suppose that q1 is d1 squared, q2 is d2 squared, and q3 equals d3 squared, just as before. Then, Archimedes' function of q1, q2, and q3 can be rewritten in terms of the d's in the following way. As a product of four terms, d1 plus d2 plus d3, d1 plus d2 minus d3, d2 plus d3 minus d1, and d3 plus d1 minus d2. This is a purely algebraic result, sort of in the direction of our previous one. All right, so again, some very nice practice for your algebraic skills here. All right, so let's start. Well, what is the definition of this A of q1, q2, q3? Well, let's use the asymmetrical form that we found useful. 4q1 q2 minus q1 plus q2 minus q3 all squared. All right, so let's replace the q's with the various expressions involving d's. So we have 4d1 squared times d2 squared minus d1 squared plus d2 squared minus d3 squared all squared. What do we notice about this? Well, we notice it's a difference of squares, because this is now a square. This is also obviously a square because it's something squared. So we can write a squared minus b squared as a minus b times a plus b. We can automatically factor this difference of squares. And it is 2d1 d2 minus this d1 squared plus d2 squared minus d3 squared times the same expression 2d1 d2 and now plus d1 squared plus d2 squared minus d3 squared. Now let's have a look at this first term. We can rewrite that. The d3 squared is appearing with a minus sign here and a minus sign here for a total of a plus sign. So let's bring it out front. And then what's left is a minus d1 squared minus d2 squared plus 2d1 d2. That's minus quantity d1 minus d2 all squared. In a similar kind of way, when we look at this, we can combine the d1 squared, the d2 squared, and the 2d1 d2 to be d1 plus d2 all squared. And left over we have a minus d3 squared. Now we've written each of these to be themselves differences of squares. Here we recognize another difference of squares. This squared minus this squared. Similarly here, that's this squared minus this squared. So again, we use the same factoring of a squared minus b squared as a minus b times a plus b. So we have d3 minus all of this, so minus d1 plus d2, times d3 plus all of this. In other words, plus d1 minus d2. And we have d1 plus d2 minus d3 over here, and then d1 plus d2 plus d3. So we factored the original thing into a product of four factors. And then if we compare that with the original statement, there's the corresponding term there. This term here corresponds to that one. This one corresponds to d2 plus d3 minus d1, this first one here. And this one is d3 plus d1 minus d2. So the theorem and proof here are taken from my book, Divine Proportions. It's Theorem 29 on page 70. So notice that this algebraic identity now incorporates the previous theorem. Because suppose that we know that d1 plus d2 equals d3. Well, in that case, this term will be 0. So this entire product will be 0. And that will imply that a of q1, q2, q3 is 0. So now we see something a little bit more. It's not just d1 plus d2 equals d3 that makes this expression 0. But also d2 plus d3 equals d1 would also make it 0. Or d3 plus d1 equals d2 would make it 0. Or in fact also d1 plus d2 plus d3 equals 0 would imply that a is 0. This is a very nice identity, which is not really novel. I mean, this kind of identity has been written down many, many times in different contexts. Okay, but we're establishing it here in the context of this language. We're giving it a name, identifying it as something rather special and interesting. It deserves to have a separate place and acknowledgement of it. Archimedes' formula, we'll call it. Here are a few exercises for you to practice your algebraic skills in relation to the triple quad formula. They're also taken from my book. Alright, so the first one asks you to show that as a quadratic equation in, say, Q3, the triple quad formula can be rewritten in this way. We can just rewrite it so that it looks like a quadratic equation in Q3. Q3 squared minus 2Q1 plus Q2 times Q3 plus Q1 minus Q2 all squared equals 0. So if we're trying to solve for Q3, say, in terms of Q1 and Q2, and we know that they satisfy the triple quad formula relation, then this is the quadratic equation that we have to solve. And here's another exercise. Show that if we have these two quadratic equations, x minus p1 squared equals q1, and x minus p2 squared equals q2, and p1, p2, q1, and q2 are just some arbitrary numbers. So if we have two quadratic equations, it can be interesting for us to ask, when is there a common solution? When is there a common solution? When is there an x that satisfies both equations? And your exercise is to show that they have a common solution precisely when these four numbers that are involved here give us a solution to Archimedes' formula. Namely, if a of q1, q2, and p1 minus p2 squared equals 0. Another appearance of the triple quad formula in the context of solving a pair of quadratic equations. Alright, so now we come to a very famous result from classical Greek geometry. It's called Heron's formula. It's named after Heron, or Hero, of Alexandria, who derived the result sometime around 60 BC in a book called Metrica. It's a formula for the area of a triangle, given the three side lengths. So if you know the three side lengths of the triangle, what is its area? It's a very practically important problem, and not surprisingly, this is a very celebrated theorem that used to be a mainstay of all geometry courses. And in fact, until relatively recently, all mathematics students would have learnt Heron's formula as part of their education. Here's the formula. The area of a triangle with side lengths A, B, and C is, here's the formula. Area is the square root of S times S minus A times S minus B times S minus C, where this quantity S is A plus B plus C over 2, sometimes called the semi-perimeter of the triangle. The perimeter would be A plus B plus C, so this is half of the perimeter. Notice that there's some quotes here. Usually you don't find quotes, okay? But for us, we have to put quotes because we're working completely rationally. Because we don't feel like doing an infinite number of operations. And this square root, unfortunately, is really asking us, in general, to do an infinite number of operations. Finding a square root is a process that goes on forever and forever and forever and doesn't end. Okay? So it's problematic for us with our logical, rational, completely clear point of view towards mathematics. Alright, so we're going to address this, but let's just carry on with the traditional way of thinking about this. Alright, so here's an example. Suppose that a triangle has side lengths, say 4, 5, and 7. Okay, then the semi-perimeter would be 4 plus 5 plus 7 over 2. That's 16 over 2. That would be 8. And so Heron's formula would say that the area is square root of, there's the S, which is 8. And then S minus A, that's 8 minus 4, times S minus B, that's 8 minus 5, times S minus C, or 8 minus 7. So inside the square root we have an 8, we have a 4, we have a 3, and we have a 1. So for a total of, well, there's a 4 here and there's a 4 here. We could pull that outside the square root to give us 4, and what's left inside is 2 times 3, or square root of 6. Okay, so the answer would be the area of this triangle is 4 times the square root of 6. And again, we're going to put this in quotes because for us, with a rational point of view, that square root of 6 represents only an applied or approximate quantity. There's no real square root of 6. This is some kind of statement about some truncation of some process. So that's a classical example of how Heron's formula would be used to calculate the area of a particular triangle if you know its side lengths. Let's have a look at another example of an application of Heron's formula. This time to a triangle whose vertices are specified to us in Cartesian geometry. So we have a triangle with vertices A, 0, 0, B, 2, 3, right there, and C, 4, 1 over here. Alright, so according to Pythagoras' theorem and the standard thinking, the lengths of the sides of this triangle are... Okay, so what's the length here? Well, I remind you that to calculate that in traditional sense, what you do is you think of this right triangle. Okay, so there's a difference between 2 in the x-coordinate, there's a difference in 2 in the y-coordinate. So this triangle, this right triangle here has sides 2 and 2. So Pythagoras' theorem, as it's usually expressed, would be that 2 squared plus 2 squared equals a squared. It tells us that a squared is 8, and a would be the square root of 8. So if you believe in lengths, if you believe in irrational numbers, if you believe in being able to take square roots, you would say, yes, this is a length, and that length has value square root of 8. I hope by now you're a little bit more suspicious about these kinds of statements, that you're starting to recognize that there's something highly problematic about such a statement, that it's assuming that there's a notion of length of a segment to begin with, that there's an assumption that there's a context of real numbers in which this length has a value, and there's an assumption that the infinite amount of work required to actually calculate this square root of 8 in the real numbers is, this is an infinity that we've actually completed and we finished, and there's the answer. Alright, so let's carry on with the thinking and let's have a look at the other two side lengths in quotes. This B here, well, it's the hypotenuse of a triangle with sides 4 and 1, so its length will be square root of 17. And again, that should also be taken with a grain of salt. And what about C, this length here? Well, there's 2 here and 3 here, so 2 squared is 4, 3 squared is 9, so we're talking about the square root of 13. So if we believe in doing an infinite amount of work, then we can look at these things and say, we found the 3 lengths of this triangle. Okay, what does Heron's formula tell us? Well, it tells us the area of the triangle must then be the square root of... Okay, first thing is the semi-perimeter. So root 8 plus root 17 plus root 13 over 2. That's the S quantity. And now we take S minus A. So if we take this thing here and we subtract A, here there's a root 8 over 2. If we subtract root 8 from that, we're going to get minus root 8 over 2. So we're going to get an expression that looks a lot like this one, except that there'll be a minus sign where there was a plus sign here. And when we take S minus B, we'll get an expression that looks much the same, but with a minus sign in front of the square root of 17. And S minus C will give us this expression with a minus sign in front of the square root of 13. Okay, and now our arithmetic with real numbers comes to our aid, and we supposedly make this calculation. We add these 3 irrational numbers and divide by 2. We form that irrational number, we form that irrational number, we form that irrational number. So each one of these operations requires an infinite amount of work. Hey, but what's an infinite amount of work between friends? Okay. And then once we've done that infinite amount of work, we multiply this irrational by this irrational by this irrational by this irrational. Another couple of infinite amounts of work. Great, and then we take the square root of all of that. we apply Babylonian method or Newton's method or something, perform yet another infinite amount of work, and we get the square root. All right, that's all, in fact, just talking, isn't it? What actually happens is that we get our calculator and press a few buttons. And our calculator is not doing an infinite amount of work, it's just doing a finite amount of work. It's just truncating up to 10 decimal places or whatever, and ignoring the rest. And it will spit out some value. And you can try it. And you will find that your calculator spits out the value 5.00000000 up to a certain amount, and then it stops. And so, in fact, there's some ambiguity. Of course, we don't know how it continues. But this certainly strongly suggests that the answer might actually be 5. And sort of makes us scratch our heads, some kind of coincidence happening here. How come all these irrationalities that we have floating around here in Heron's formula somehow magically seem to be canceling themselves out or disappearing to give us this nice, seemingly rational, even integral value? Well, it's not really a surprise when we look at it from the point of view of the geometry of the original question. Because remember, when we were talking about the area back in Math Foundations 33, we discussed exactly what the area of a triangle like this should be and how we should compute it. And we found that we could view that completely arithmetically and rationally. For example, we could think about a rectangle that encloses the triangle, and we could compute the area of that rectangle, say that would be 4 times 3, that'd be 12. And then we could subtract the area of this thing, which would be 4 times 1 divided by 2. That's 2. We take the area here, which is 3 times 2 divided by 2. That's 3. And the area of this one here, well, that's 2 times 2 divided by 2. So that's another 2. So we start with 12, and we subtract 2, and we subtract 2, and we subtract 3. So all together we're subtracting 7. So yes, we should get 5. We can see that geometrically the area is 5, and Heron's formula is somehow using a lot of irrationalities which magically kind of cancel themselves out in some mysterious fashion to get that same rational answer, even though it's not clear that it's rational from the Heron's formula. Heron's formula doesn't immediately suggest to us that this is actually a rational number. From linear algebra, there's another way of thinking about this area. We have two vectors, vector 4, 1, a vector 2, 3. In linear algebra, we learned that to find the area of a triangle, we take a determinant. The determinant of this little 2 by 2 matrix, which is 4 times 3 minus 1 times 2. We divide it by 2, and we get 5. This formula, in not exactly this form, but in the equivalent form of AD minus BC, we established also in this Math Foundations 33 lecture, if you'd like to have a look at it. So there's something curious going on, something that needs explaining. Why is it that in this context the irrationalities of Heron's formula somehow magically disappear? It's suggesting that we don't really understand what's going on, that perhaps Heron's formula is not entirely the right way of thinking about this particular situation. That turns out to be exactly the case. So to understand what's really going on with Heron's formula and how we really ought to think about this fundamental theorem, let's go to planar geometry and establish just a few notions, basic notions about measurement in the plane. All right, so suppose we have two points, A1, which is A1, B1, and A2, which is A2, B2. These are now points in a plane rather than points on a line. We can define the quadrants between these 2 points in a very analogous fashion to what we did in the one-dimensional case. We can take the difference between the x coordinates, the first coordinates, A2 minus A1, and we can square that. And we can take the difference between the y coordinates, or the second coordinates, B2 minus B1, and we can square that. And we can add those two squared quantities. And we can call that Q of A1, A2. Now that's sort of familiar from Pythagoras' theorem. Okay, that's sort of one step in finding the traditional distance between A1 and A2. This quantity is a purely algebraic and symmetric quantity. There's no absolute values involved. Even better, there's no square roots involved. Just addition, multiplication, and subtraction. And it's symmetric. If you interchange A1, A2, this quantity does not change. Now in standard modern mathematics, you don't even learn this definition of quadrants. The notion is not even defined. It's absolutely incredible. Okay? Instead, what one does is one defines the corresponding irrational quantity obtained by taking the square root of this quadrant. So you will all know that the distance between A1 and A2 is defined to be the square root of the quadrants. Well, actually, it's usually not defined this way. It's usually defined in this formula. That we take A2 minus A1 squared plus B2 minus B1 squared, and we take the square root of that. And when I say we take, okay, this means very liberally we take. We perform some thought experiment that involves performing this infinite operation to the very end, and then we take that big result of that completed infinite operation, and there it is. That's called the distance between A1 and A2, and this is considered a fundamental notion in modern geometry. Even though it self-evidently involves an infinite amount of work, and in any particular case, it can only be exhibited approximately in general, unless you choose your triangle very carefully. Ironically, what we're calling the quadrants is often called the squared distance. So modern mathematics logic is so impoverished, right, that the absurdity of taking a quantity, finding its square root, and then referring to the original quantity as the square of the square root is not widely appreciated. People do not roll their eyes at the mention of the squared distance, even though they probably should. This is almost absurd. This is the fundamental algebraic notion. This is some perverted, transcendental, infinite version of it. It may very well be useful in applied mathematics, sure. But what we really mean is that approximations to it are useful in applied mathematics. But in pure mathematics, this is a highly dubious notion. Even its definition is highly dubious. All right, so now we have this notion of quadrants. And now let's have a look at Heron's formula from a different perspective. All right, so very exciting. We're now moving towards a much better formulation of Heron's formula. First of all, we have to admit what actually is the problem with the logical weaknesses in Heron's formula. It relies on a theory of real numbers because square roots are involved. It relies on a theory of lengths, which for general segments is problematic, also because of the need for square roots. For triangles in the rational plane, the irrationalities in Heron's formula are or appear to be unnecessary. And in fact, also, if you look at proofs of Heron's formula, they often involve other transcendental circular functions like cosines and sines and so on. So the logical difficulties with those things are also incorporated. So by adopting a logical or rational viewpoint, we naturally ask, is there a better formulation? If you have a real number, irrational numbers are okay kind of point of view, you don't ask to question this. You just say, okay, that's the way it is. Okay? But if you have a rational point of view, then necessarily you are going to be unhappy with anything that involves square roots, especially fundamental formulas. And you're naturally going to ask the question, can we do better? Can we move to a higher level and see this formula in a better, more algebraic, more general light? So in fact, we can. There is a better solution. It's called Archimedes' theorem. We're going to call it Archimedes' theorem. It's more general, it's more logical, it's more algebraic, and it's more computable. So, what is this far superior form of Heron's formula, which we are now going to call Archimedes' theorem, in honor of Archimedes, who was really understanding Heron's formula before anybody else, but in work that is lost to us. Okay, so what is this formula? So here it is. The area of a planar triangle with quadrants Q1, Q2, and Q3 is given by this expression. 16 times the area squared is Archimedes' function applied to Q1, Q2, and Q3. So in other words, it's the difference between the left and the right hand sides of the triple quad formula. So we see that the one-dimensional triple quad formula, which originally started as just a relationship between the quadrants formed by three collinear points, contains the algebraic essence of a fundamental two-dimensional result. When we get to a triangle in the plane, this same relation that occurred first in the one-dimensional case is exactly what we require to get at the area. Well, actually, to get at the square of the area. And there happens to be some constant 16 here, which is sort of an accident of the normalizations that we've chosen. So this is a very interesting point, okay, and I think it opens up all kinds of possibilities that a situation in one dimension somehow points the way, leads us to the right notions to understand something fundamental in a higher dimension, namely in two dimensions. This is a very interesting possibility that maybe we can discover lots of things in higher dimensions by understanding what's happening in lower dimensions well enough. Okay, we're going to see this as a very nice insight. So now let me show you how to go from Heron's formula, we'll transform that to derive Archimedes' theorem, going from something irrational to something rational. Here is Heron's formula. Again, the area of a triangle is the square root of s times s minus d1 times s minus d2 times s minus d3, where d1, d2, and d3 are the side lengths of the triangle, and where s, the semi-perimeter, is d1 plus d2 plus d3 all over 2. So we're going to take this formula and we're going to rewrite it. First of all, we're going to square both sides. So the area squared is now just the product of these four terms. There's no more square root. Now s is just d1 plus d2 plus d3 over 2. What about s minus d1? Well, if we take this thing here and we subtract d1, then we get d2 plus d3 minus d1 over 2, which we'll write this way. We've seen this kind of thing before in that example that I did explicitly. When I take s minus d2, I'm taking this and I'm subtracting d2. The effect is that that plus sign there changes to a minus sign. And when I take s minus d3, I get d1 plus d2 minus d3. Okay, so the 2 times 2 times 2 times 2 gives us a 16. And the product of these four terms, that's exactly Archimedes' function of q1, q2, q3, where q1, q2, and q3 are the squares of d1, d2, d3 respectively. That was exactly what we called Archimedes' formula. The fact that this particular product equals this Archimedes function of the squares of the d1, d2, d3. So it's almost an immediate consequence of Archimedes' formula. The fact that 16 times the area squared is A of q1, q2, and q3. So we see that Archimedes' theorem is a rational form of Heron's formula. Now this is, in my view, not an adequate proof of Archimedes' theorem, because I don't accept the validity of Heron's formula in the first place, because I don't believe in those irrationalities upon which it depends. So ultimately, we're going to have a separate, completely rational proof of Archimedes' theorem. At this point, I just want to clarify to you that it's the triple quad formula which is ultimately really responsible for giving us something like Heron's formula, which namely the improved version of Archimedes' theorem. 16 times the square of an area of a triangle is given by the Archimedes function of Q1, Q2, Q3. And I remind you that this A is Q1 plus Q2 plus Q3 all squared minus 2 times Q1 squared plus Q2 squared plus Q3 squared. So let's see how this improved rational form allows us to reconsider the examples that we looked at earlier. So let's have a look at this triangle with side lengths 4, 5, and 7 that we looked at previously. The associated quadrants will be the squares 16, 25, and 49. So according to Archimedes' theorem, 16 times the area squared is A of 16, 25, 49. And that's 4 times 16 times 25 minus 16 plus 25 minus 49 all squared. All right, the 4 times 25 is 100, so we're going to get 1600 there minus, here we have 41 minus 49, so that's minus 8 all squared, same as 8 squared. And then that's 1600 minus 64, so 1536. And if we divide by 16, then we find that the area squared is 96. I remind you that the area was then the square root of this, which was 4 times square root of 6. But we see also that really rationally it's the square of the area that is more natural than the area itself when you have a triangle given in terms of side lengths. The other example that we looked at was a particular triangle ABC, with A being the point 0, 0, B the point 2, 3, and C the point 4, 1. The quadrants of that triangle were 8, 17, and 13. So the lengths or the distances of the triangle were the square roots of those things. Here we're just dealing with the sums of squares without taking square roots. Vastly simpler. So according to Archimedes' theorem, 16 times the area squared is A of 8, 17, 13. And just doing a slight variant on what we did before, I'm going to choose 8 and 13 as sort of the pair that we're going to bring together. So it's 4 times 8 times 13 minus 8 plus 13 minus 17, all squared. All right, so this is 32 times 13. Here we have 21 minus 17, so that's 4 squared, or 16. If we divide by 16, then we get that the area squared is, okay, divided by 16, that becomes a 2. So 2 times 13 is 26. 16 divided by 16 is 1. So we get 25. And finally, the area equals 5. And we are not surprised that it's something rational. It should be something rational because we're starting with points with integral or rational entries in the plane, so the area should be rational. And we've completely avoided any irrationalities. We see now that that whole story with taking all those square roots and taking all those distances and making all those irrational calculations that in fact we can't actually do, having to resort to a calculator to spit out 8 or 10 decimal places, it's all something of a red herring. It all represents a misunderstanding of the essential nature of what's going on. The essential nature is completely algebraic and contained essentially in this Archimedes formula, which is really essentially the manifestation of the triple quad formula. Very important insight. So this is rational mathematics. All right, so much to be thought about in this lecture. Heron's formula has been a mainstay of geometry for thousands of years. It's something that students all used to learn. We can now see that they probably weren't looking at it the right way. The manipulations behind what I've been doing here are not unfamiliar. They are not original. We can see them in various forms in many, many places. So in some sense, many people have rediscovered over the years the kind of essential algebraic aspect of what's underlying what we're talking about here. I guess the novelty here is to put things in center stage, to give things proper names, and to identify clearly that this is really the right way of thinking, that the square root business represents a misunderstanding of what's going on. Okay, so this is a very profitable way of thinking. Next time we're going to carry on and look at some other aspects of how the triple quad formula and variants of it, extensions of it, connect with classical geometry. We're going to go back to the ancient Indians, and one of the most remarkable results of ancient India, Brahmagupta's formula for the area of a cyclic quadrilateral. And we're going to see that that too is curiously and intricately connected with one-dimensional affine geometry. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.